So we'll start with the, for a little review, we'll start with example number 6. So in this example, I'll actually pull up the R code. We had two groups. Well, sort of the top part of this code sets things up so we're generating data for two groups, y1 and y2. We're generating equal amounts of observations per group, but that's not really pertinent. The code will work regardless. We're generating them with equal sort of error variance per group. So this is an example of IQ. So we have an error variance of 15 for the sort of data generating populations. And here we have the mu value, the sort of the mean, as being different between these two groups. So that instantiates the simulation of a scenario where you actually do have two truly different populations with these, with the difference between them being about 11 IQ points. But we're observing two samples from those populations, and we don't really actually know. We're pretending not to know that they differ by precisely 11 points. So we can generate that data, and then it's less typical to have data in the format where you just have like one vector for one group, another vector for another group. Much more frequently, we have it in what's called long data format. So for some reason, this got we must have been playing with this last week. So, but to show you what long data format would look like is this. So I can say, well, I'll make it big. My data. It would look something like this, where we'd have, for each observation, the corresponding group for that observation. We added on this thing x, which is just a numeric encoding of what is in this group column. So for A, it's always going to be -5 and -0.5, and for B, it's +0.5. And that's going to be useful because we can reflect, well, when we get to the code, I'll show you why that's useful to have it as these numbers here. So when we package this up for Stan, I guess this particular code for packaging it up didn't have long data format. So it just said, okay, the number of observations, I'll even just change it so that I'm pretending that we're starting with long data. So number of observations for y is going to be the number of rows in my long data. Y should be my long data y, and x is my long data x. So that's an alternate way to package up the data. We'll compile. In theory, that's compiling the model. And I'll change the sampling iterations down to 2e3. So while that's compiling, we'll look at the Stan code. So again, the Stan expects just a single number coming in to tell us how many rows of data there are, and then two vectors of length, this number that we gave it, y and x. So way down at the bottom, we see that y is here in the model. We're saying that y is distributed, has a normal distribution with some mean here and some standard deviation here. So the standard deviation is modeled, is sort of initialized here in the parameter section, sigma. And we can see down here, we express the prior that we have on sigma. We put a Cauchy distribution on that. I told you last week that the Cauchy is just a t distribution with the degrees of freedom of 1. So it looks kind of like the normal distribution, but much fatter tails. And because we explicitly initialized it as a lower bound of 0, it's not going to, this prior means implicitly is cut off at 0. So it will never have negative values for this standard deviation, which is what we'd want. Because if you have negative values for a standard deviation, well, that's not sort of a defined concept. So what this is saying is that all the observations for y are modeled as coming from some normal distribution, which could vary, which could have a different mu, and we'll talk about mu in a second, or mean. But regardless of what this mean is, they're all going to have some common error scale, standard deviation. So the two groups are not going to differ in terms of the standard deviation they're given. And furthermore, individuals from one to another will have the same standard deviation. Indeed, they're only ever sampled once. So the other variables in this sampling definition for y, we've got mu, diff, and x. Well, x is this thing we put up here as another sort of piece of input to the data, or input data to the model. So what we're saying, first of all, let's take this mu. This is the intercept for the model, so we notice here it's just additive with x, so it's there no matter what. And in this parameterization of the model, we have that x causes the score to go either up by diff times 0.5 or down by diff times 0.5. That's why we had x as being plus 0.5 or negative 0.5. So diff reflects then the difference between the two conditions. So this is that center difference parameterization we talked about the other day. So mu is the center of the two groups. We're assuming that, or we express a prior on it that is centered on 100, an IQ score of 100, but we express our uncertainty about that prior by having a variability around that 100. So with a standard deviation of, well, normally distributed variability around 100 with a standard deviation of about 20. And additionally, we have the diff parameter. We expressed a prior on that diff parameter. We don't know whether one group is going to be have a higher score or otherwise, so a good sort of general first approach is to just apply a prior centered on 0. And then we obviously don't know whether, well, we express uncertainty that we don't want to express that we know it's precisely 0, so we have some uncertainty about the magnitude and the sign of the difference. So we say that the difference prior has a normal distribution centered on 0 with plus or minus 20 as the standard deviation. So when we have our compiled model, which hopefully it's all compiled, I'll go back to the R code. We've set the number of sampling iterations. And as I recall, this model actually compiles really quickly. Samples very quickly, so I probably could have left it as the large amount of iterations I had there, but I'll leave it as is now. We run this little bit, which takes the data that we packaged up for the model. I'm asking for just one chain. Usually when we're doing inference in the Bayesian world, because there's some randomness about how things, at least the sampling initially starts off, it's a good idea to run it multiple times from different starting points. Each of those times are called a chain, so you can sort of amalgamate the results from multiple chains to make sure all the chains basically came to the same conclusion. Otherwise, again, I said it was a sort of random iterative process, so you have to tell it how many iterations you're going to do, so that's where we get the sampling iterations. There's a sort of a unique starting process that's where it sort of just generally explores the sample space that's of the model, or the parameter space of the model, and the length of that initial exploration is defined by this warm-up argument. And finally, if we want to get some updates as it's going along for particularly slow models that we'll see in a little bit, we can ask for these updates to occur at some refresh rate. And finally, because, again, there's randomness associated with these models, it's a good idea for replicating your results down the line to explicitly supply a random seed. You'd want a different random seed per chain you run, but if you put in, if you ask for multiple chains, it would do that automatically. So I'm just going to ask for one chain. I'll run this, pop over to my R window. Oh, I hadn't run this one. All right, variable doesn't exist. So what did I do wrong? I'm going to press undo until I see what I have done differently in this. Oh, I wonder if... Let's take a look. So we packaged up the data. We've got a list with components ny, y, and x. And this is the data here, ny, y, and x. Let's look at that error, because I thought it said something about variable and x. Did I literally just name it wrong? Yeah, it should be ny. Do I have it as the right... Oh, no. Ha. I had the wrong path. I already had this R console set up, and I had forgotten to set the path, so it compiled the wrong code. So I'm going to, in my R code, I'm going to ask it to explicitly set it to the code we're looking at. Give it a recompile. While this is going, any queries so far on the structure of the model? Come back to here. Just wait. I can look at my CPU usage monitor up here to see when it's done compiling. If you have, so this is, my machine is a 4-core, it has 4 unique processes available to it to do stuff. When you compile, you can actually use all of those cores. When you sample, you can only ever use one. But if you've got a more beefy machine, Marian has a machine with more cores, so she'd, in theory, be able to compile faster. There's a computer downstairs with, I think, 8 unique processes available, so that would make it compile really fast. All right, so that sampled super quick. So let's actually take a look at the samples that it observed and compare these sort of values to the values that we used in generating the data. Well, when we generated the data, we didn't use the center diff parameterization. We just generated 2 different groups of data. But we can sort of do the math to infer. So the center of these 2 groups, 97, 108, this should be around 101. So if we look at that, 104 is the center, but this credible interval thoroughly encompasses the actual center that we instantiated in the by simulating the data. So we've recovered that parameter nicely. The difference between the 2 groups, we have sort of a real difference of 11 points, but then we forgot about that real difference and asked it what we should think the real difference is given the data, and prior that the real difference was 0, and it indeed has come up with a posterior distribution of beliefs that is centered on what the real difference is. So we've recovered that one nicely too. Critically, with a credible interval that excludes 0. So 0 is not really a credible value for going forward on our beliefs for this, I guess, the data generating populations. In our model, we also had another variable that we're not so much interested in, but it's part of the model, so we get samples about it, which is sigma. And sigma we had the data generating as if the true value were 15. And when we look at the output, it's 13, and the credible interval thoroughly includes it. It's maybe a little bit underestimated, and that may be because the Cauchy is maybe not a great distribution for the error variance, because the Cauchy, as I said, is symmetric around 0, but cut off at 0. So the highest belief is at a value of sigma for 0, which actually isn't a really realistic expression of our beliefs. We don't actually believe that the true data generating populations are most likely to have the standard deviation of 0. So it would have been probably a better idea to do something like have a log normal distribution of belief on that. But your inferences generally aren't super sensitive to the choice of the error variance prior. So that's as even shown by using this pretty unrealistic prior here, has still recovered the parameters for the main parameters of interest decently. So that's a scenario where you just have sort of two groups, one manipulation, but it's very often that you actually have not actually more groups, but more variables that are manipulated, and so you need to have more parameters in the model. So actually, I'll still pull up this same model that we were looking at. So when you have one group, or one manipulated variable, that being the group, and two levels of that variable, you'll have two parameters that you have. In the center diff version of this model, those parameters are the center, mu, and the difference between the two groups, diff. If you had two manipulations, each with two levels, then you'd have then you'd have to have four parameters. In the center diff parameterization, you'd have sort of the mean of all the groups, the difference caused by being in level 1 of variable 1 and versus level 2 of variable 1, and then another one being the difference between being in level 1 of variable 2 and level 2 of variable 2, and then finally so those would be the two main effects contrasts, and then finally a contrast reflecting the potential interaction between those things. So if we actually jump forward to the 2x2 code, so that's in section 10, pull up the R code, and I'll pull up the RStan code. So pulling up the R code, let's actually run through it. So I'll clear the workspace, generate data. Here in the data generation phase, you'll see that I'm explicitly defining 3 contrasts plus an intercept. So we have a model with 4 parameters. And when you get to more complicated models like this, it becomes a little bit cumbersome to use the strategy that's used back in the old number 6 code, where you actually give each parameter its own name, and much, I guess, easier, and it turns out some of the computations are faster when you do it this way, is to use a sort of matrix notation for holding the variables and doing the math. So here we're giving it a matrix for x. So x here is generated by having these contrasts and then turning it all as a data frame and then turning it into a matrix. But let's just take a look at x. So it's just we've got one column with all ones, another column corresponding with the value for what should be the main effect of here I've got them labeled as one variable is denoted, I guess, A versus B. Another variable is denoted as 1 versus 2. And so contrast 1, I think, is A versus B. And contrast 2 is 1 versus 2. So, and then contrast, the interaction contrast is just coded by the multiplication of the two main effect contrasts. So what we get out is this matrix X. So in the prior version of things, we'd actually have to give it I guess, 3 vectors: contrast 1, contrast 2, contrast 3, and intercept is just something that we'd have as we don't need to input it. Now we've got an explicit matrix that has an explicit intercept column, and then the 3, what we would have given it as 3 vectors in the prior version. So that's our X. Y is exactly as before, just a big long vector of the Y values. And we have to tell it how many X values, how many columns there are in this X, simply because that's necessary for doing the initialization of this matrix. The ditto, we have to tell it how many columns, or sorry, how many rows are in how many Y observations we have. So in terms of parameters, what we're going to do is, again, instead of separate values for, okay, here's the intercept parameter, here's the contrast 1 parameter, contrast 2 parameter, contrast 3 parameter, we just have a vector that is 4 items long that we'll just call beta as a shorthand, as a useful name. And that will just be a nice collector object for those values that we otherwise would have had as separate parameters. Intercept, contrast 1, contrast 2, contrast 3. Otherwise, we still have that sigma parameter in there. And sigma is treated exactly before. So we have our Y data coming in. It's distributed normally with sigma standard deviation. We've got this probably unrealistic Cauchy prior for error, on sigma. But what's new here, again, because we have this single vector for the all the contrast, the intercept and all the contrasts of interest, we have slightly different format for how we express our priors for that, and then also slightly different format for the math down here in expressing for each sort of value in Y what should be here for the mean that we're modeling as it being a sample from. So the way we've just set up this matrix is the first column is is all just ones, and that's the center point or intercept column. So we want to explicitly say that that column has a normal. I guess we wanted to have a prior that's centered on 100. I remember this from before. We modified these because 5 is a little bit too certain a prior for this sort of data. So we'll modify that to have a prior centered on 100 with normally distributed certainty of with the standard deviation of 20 IQ units. And then for all the other contrasts, so the main effect of group A versus group B, main effect of group 1 versus group 2, and the interaction between those so this syntax here, we're looping over the remaining columns and saying that for the second column to the last column, just apply the same normal prior centered on 0, so we don't know whether these contrasts will have a positive or negative effect, and we don't really know what the magnitude is, so we'll have a pretty broad range of sort of reasonable beliefs about the magnitude. And so that yields us, again, we have this vector beta and this matrix X, and it just turns out the way the math works, simply expressing the matrix X times the vector beta we'll go through and work out the math that would be equivalent to having, let me bring up this, yeah, I'm going to bring up the 6 again. Well, actually here, I'm going to take this, copy it, and comment out what the copy is, and I'll show you. It would be the same as saying x, or same as saying mu plus contrast 1 times x. I guess it would be x column 2 plus contrast 2, x column 3 plus contrast 3, x column 4. Yeah. So the piece of code that I don't have, so again, these are using the names that we would have used if we did it the non-matrix way. Since we're doing it the matrix way, we don't have a variable called mu or a variable called contrast 1, contrast 2, contrast 3. But also clearly this line is much longer, much more to type, and many more mistakes that you could be making in typing there, so it's just easier to do it this way. There's also some just computational benefits when it does the sampling. Not noticeable in these small examples we're doing though. So that in theory, I guess, could have been compiled. I didn't make any changes other than doing this comment. That should be the case. Oh yeah, I did. So I'll leave it. So going back to the R code, I can. Oh, I guess. Oh, I remember at the end of the class, it was asked that I actually show what this sort of 2x2 type of data would look like in long data format. So I actually did some code here to show what it would look like in long data format, which is useful to show you. So it'd be something here where you'd have 3 columns, 1 column showing y, 1 column showing var1, 1 column showing var2. And it was also asked how I would get that into the, how I'd compute the contrasts given data read in like this, which is pretty standard for how we have data. So x could be computed as follows. Again, intercept is easy, just 1 in all the rows. The contrast 1 column, if you take a variable that's a factor, which we did automatically converted things here, and immediately turn it into a number, the first level of that factor will be called 1, and the second level of that factor will be called 2, regardless of what the factor labels are. Here we had A and B for var1, but we'll still get a 1 and 2 out of this by just immediately converting it to a number. If we have 1s and 2s, it's easy to turn those into negative 0.5s and 0.5 by simply subtracting 1.5 from all the values. So we can get that X matrix by simply converting the factor levels in this manner, and then finally the third contrast by, again, multiplying those factor levels. So here is packaging up. This could have been done from the original data where we had ny as just the combined length of all these things, or we can say n row my data, since that's the long version of the data. An x, well, we created x, that's there, there's x, and y, we could just say my data y. Call it capital Y. What do we do? Yeah, capital Y. So package up that data for RStan. I'll double check that I set the place. No, I didn't set the working directory. So now let's set to the right working directory, and we'll compile. While that's compiling, I'll look down a bit to make sure this stuff is decent. So if you had, so this is a 2 by 2 example. Again, between groups, if you had a 2 by 2 by 2 example, it would just be a simple extension of this idea. You'd have 3 contrasts that you just define here. You'd have a third one. So 3 equals 9. Whatever your var 3 was. And then when you have 3 variables, there are 3 potential interactions, 1 and 2, 2 and 3. So this would be, and then 1 and 3. And then finally you have the 3-way interaction. So it's easy to extend this example to the scenario where you have more manipulated variables. The example where the folder where it's talking about 3 groups, that demonstrates how you'd extend to having more levels of one of the variables, but otherwise it should generally all, it's a generalized approach. Okay, so now that we've compiled, we can run. See if I can get back fast enough to see it running. Oh, yep. Maybe I'll stop and actually pass it for here for purposes of this demonstration. As I recall, it samples very efficiently. All right, so we'll look at our outs, and I said it samples pretty efficiently, and indeed it seems that all these, the effective sample size is pretty high for all these things. We asked for 1,000 post-warm-up draws, and so for this one we've got nearly 1,000. So pretty, and for all of them they're pretty, well, all the things that we care about, it's pretty decent effective sample size. And looking at the things that were generated, we can compare those to what we actually asked it to do. The sort of data generating population variables that we simulated, from which we simulated the data, and compare those. So the general difference between A and B. Well, A, this has a mean of, what did I say, 102? Yeah. And this is going to be 100, so it should be, well, there we go. It's centered right on 102. And there's a credible interval around that. Ditto the difference between 97 and 100, I guess the average of that, so that's going to be 98. And the average of these two is going to be 104, so 98 to 104 is about 6. Sorry? Well, the critical one is the third one. That's the easiest to look at. Oh wait, yeah, this was the intercept, right? Okay, so yeah, the right. So the average, the center of all these groups is about 102. Contrast beta 2 is contrast 1. Beta 3 would be main effect, would be contrast 2, which is the main effect of 1 beta 2, and beta 4 is the interaction. And most critical here is that we explicitly had an interaction whereby there should be no effect of 1 versus 2 in level B, and there is an effect of 1 versus 2 in A, and if we actually look at the magnitude of the effect, it's about 11 in A and 0 in B, so the interaction contrast should be about 11, and indeed it comes out to that. The sign depends on how you coded which things negative 0.5 and which thing is positive 0.5. And we can actually explicitly take a look at the condition means instead of this center diff parameterization by grabbing the samples, and we'll flip down here to actually compute what for each sample, what the actual parameter value is for each of the groups. So for the first group, you've got the intercept, beta 1, plus the main effect of A versus B, so that's beta 2, times negative 0.5, because we had labeled A as negative 0.5 up in the specification of the contrast. And then the main effect of 1 versus 2 times negative 5, and then the interaction between 1 versus 2 and A versus B times 0.25, because when we did the interaction contrast, we said the interaction contrast was simply the multiplication of these two contrasts. So that gives us group 1, and ditto, we could iterate through and get all the other groups. You can see that gets us all the predictions for each group. You can look at each group. So there's A1, it's 95% credible interval. There's a 95% credible interval for group 2. We could look at the differences between all the groups. So critically, A1 versus A2 has this difference. B1 versus B2 is generally centered around 0. And there's other differences that you could do, but they're not as interesting. So A1 versus B1 and A2 versus B2. But they're not really, mathematically they end up having the same information, but they're not as sort of straightforwardly informative as this, showing that A1 versus A2 has this nice effect and B1 versus B2 has no effect. So that's where we left off. And I said that we'd talk about neater models. So I had sent actually an email that had these models, as well as so it's the code for the models, as well as the actual models compiled, and a bunch of samples from the model. So this should be a little bit faster than last time. So I'll start by run a little key code command that automatically sets my working directory to the current place. I'll run this. So what we're going to work with now is hierarchical models. So we dealt with scenarios where you just had simple between subjects manipulations. We could work through a bunch of within subjects manipulations, but those are, I guess, they're less sexy than we typically have data that's hierarchical. We often compress the data down to simple within subjects designs, but we ignore the hierarchical nature of the data. There's a lot of information there in the hierarchical structure that we're getting rid of, and we may be making some inferential errors when we ignore that data. So I thought I'd jump straight to the hierarchical cases of having within subject variables. It's also the case that I actually haven't figured out the simple within versions of things yet myself, so because I, of course, jumped straight to the more complicated hierarchical within when I started learning. So what do I mean by a hierarchical model? Well, it's somewhat demonstrated here. The general idea is that you have a population of people, and those population of people may have, let's stick with the concept of IQ, because I think I use IQ-ish numbers down here when I generate data. People are going to vary from one to another on what their IQ is. Let's say you do some manipulation, and they may vary from one to another in their response to that manipulation, regardless of what their IQ is. So when you talk about people, there's two numbers. Each person has two numbers. One is their sort of general overall IQ, and the other is the degree to which they manifested some effect. And people can vary from one to another in those values. Now, when you have a scenario additionally where, well, you can have a scenario additionally where instead of trusting the IQ from a single test, maybe you have a whole bunch of different tests of IQ that are supposed to generally converge on the same number, but may have a little bit of variability. So you measure a person at time 1, so before manipulating your IQ affecting or supposedly IQ affecting intervention. You measure them a bunch of times. You get a bunch of IQ scores for a person at time 1, and you get a bunch of IQs for a given person at time 2. So we therefore have a number of people, and for each person, 2 conditions, say time 1 and time 2, and within each of those conditions, a number of observations. So where before, so I like to talk about n and k in referring to the numbers of things. So n is the number of people that we have, and k is the number of observations per condition per subject. 5 is probably a little low for what we typically do in psychology. If we were doing like a reaction time experiment, we'd want that to be at least like 20 or ideally 50 observations per condition per subject. But we'll just deal with 5 for now. Remember I said that we observe per person, per condition, we make many observations. The standard in the, it's possible that people can vary from one to another in how variable their performance is. Indeed, that's very likely the case. So it's, young, healthy adults tend to have nice low variability in their performance. Very younger kids will have higher variability in their performance, and older adults may have larger variability in their performance. And even within those groups, there may be differing amounts. One person may have high variability, one person may have lower variability. And I could talk about actually capturing those differences in variability in models in a little bit, but for the current scenario, we're going to do what is common amongst most of the mixed effects models, hierarchical models you'll have possibly seen so far, which is just assume everybody has the same amount of variability. It tends not to actually matter in the end whether you try to account for those differences or not, because again, the precision in your modeling of this error variance variable or parameter doesn't tend to affect your precision in modeling the variables that you're actually interested in. So what we're doing is we're going to assume everybody, when you make an observation, will have a general error variability of a standard deviation of 10. We're going to say that everybody is coming from a population with a sort of a mean IQ of 100, and everybody is coming from the same. That when I say that people are coming from a population with a mean IQ of 100, the standard deviation of that population is 15. These could be any numbers. I'm just choosing numbers that are consistent with their knowledge of what IQ is like. Again, we're simulating data here. These aren't anything to do with our priors. And I'm going to simulate data such that I'm going to have some manipulation with an effect of 10 IQ units, pretty big. But people vary from one to another in the magnitude to which they manifest that effect. So, and that variability will be characterized by a normal distribution with a mean of 10, but variability of 3 IQ units. So what I can do is I can generate a whole bunch of intercepts for subjects and a whole bunch of effects for subjects. And then I'll combine them to create actual observations for each subject. So I want to get 30 intercepts. So we've got the intercept mean here as the mu argument to R norm, and the intercept SD as the sigma argument to R norm. So that will give me 30 intercept estimates. I haven't run this. But,
and so the intercept is essentially capturing variability between people.
Yep. It's really the reason why we do within subjects manipulations is because we know there's some variability just from one person to another overall that we don't actually care about. And so by having the same person measured many times, measured once per condition of interest, we actually can subtract out that variability of one person to another in terms of their overall score and narrow in on the variability of their overall, of the manipulation of interest. Yes. Yeah, yeah, I'm just generating data so that we can then forget all these numbers and just have a data set. Yeah. Yep. Yep. So we're just generating fake data. I'm walking through how we're generating it because I want you to see what the structure of the data is that we have. This is the typical sort of what would be considered hierarchical data set. Really, I'm also walking through the assumptions of a hierarchical model. That is that we have data that has sort of where people are normally distributed in terms of what their intercept is, and people are normally distributed with regards to what their effect is. So if I go to R, I just want to see where I am. So if I look at S-intercept, it's just a bunch of numbers. It should be generally, it's hard to see with 30 observations whether it's normally distributed or not, but we'll trust the random number generator in R. And then if we have an effect, each person will have S. So the first person gets an intercept of 90 and an effect of 14. Second person gets an intercept of 102, an effect of 9.6. In order to generate the data that we get from a person like this, so let's say we have a person with an intercept of 90 and an effect of 14. Well, we go and observe them. So that's what this little bit is doing. It's iterating over people, and it's collecting together data from each of those people that we iterate over. So for each person, we go in and we combine the data that we already have with some bunch of new data. So what is the new data? Well, it's that person's, so I guess, for the one person, sub num will be 1. So we grab intercept number 1 and effect number 1, and for condition A, we generate k observations. Up here we had k equals 5. With a mean of this, so their intercept minus the effect divided by 2, and a sigma that we specified up here. So this sigma, you see it's not subsetted in any way or different from one subject to another. So this instantiates that assumption of common error variance for all people. But for condition A, they get a mean of this. And for condition B, they get the mean, which just looks very similar, but instead of minus subject effect divided by 2, I get plus subject effect divided by 2. So that means that the two conditions A and B should differ by precisely the subject effect. So that would get the data for the first person, then it comes to the second person, and it gets the second person's values here. So again, this is just generating data. Once we generate the data, we'll forget what these true values are and what these subject true values are. So having generated the data, collected it all together, I'm going to factorize, and we can view the data in viewer. Let's see. I don't really like this. What's it called? X11 data viewer. I actually prefer to just literally just say data in the console, and I can scroll through. So for each person then, so we've got a data frame with 3 columns. ID, which is just a arbitrary name I gave to the subject number, partially because it's easy to type. Condition, and we see that there's A's and B's in there, and value. And critically, we see that each person is observed for both A and B. And let's observe, pardon me? Yep, exactly. So 5 times for A and 5 times for B. Now we could have had a scenario where each person, say, person 1 was 4 times for A, 5 times for B, person 2 was 3 times for A, 6 times for B, person 3 was 10 times for A, 2 times for B. It doesn't actually need to be precisely neat numbers of, precisely the same numbers of observation per condition per person. The analysis, the RStan code will work regardless of that, but just for data generation, it was easier to generate it nice and symmetrically like that. So having created this data, we need to create some contrast. Now this is a simple sort of design where we only have one experimental manipulation, so we don't really need to do the full matrix coding of things, and indeed we're not going to for this particular example because I want to walk through. It's a little bit easier to see what needs to be done to account for the hierarchical structure if we don't do the matrix stuff yet. So we'll define that function that creates the contrasts, and we'll package the data for Stan. So we're grabbing NY is the number of rows in data, and S here, that's a little bit new, the number of unique entries in the ID column. That's the number of subjects. Y is the column that's the actual observed data, the values column. Contrast, well, I just convert that condition column to negative 0.5 and 0.5. And S is the name for that I'm giving to the vector and Stan that's going to have the actual subject IDs in them. So it needs to run from 1 to the number of levels of ID there are. So that's why, even though the actual labels are 1 through 30, it's good practice to, again, turn that into a factor and then turn it back through ASVAC numeric to make sure they're sequential. I will start compiling. Oh no, we don't need to compile because I already did that. So I can tell R to just stop. Well, let's look at the actual data while it unnecessarily compiles. The RStan file, while it compiles. So we have the data definition in place, and it's the same as before. A little bit new is that I put these things lower and upper on here. They're absolutely unnecessary. It just conveys the general idea that it's expecting a scenario where you have at least one observation of data, you have at least one person, and once you've said what the number of people are, you expect it to have values in the S column that range from 1 to the number of people. It will work exactly the same, give you all the exact same numbers if you didn't have that there. This is just me being a little bit pedantic. We gave it a vector called contrast, and that's that condition contrast, that single condition contrast, and a vector called Y for outcomes. So for parameters, we have good old sigma. And if we skip down, we'll see that sigma, oh, that may be one reason why I had really slow sampling in this, because so as I said before, I actually pre-compiled these models and I also pre-sampled them to save time for us. I had noticed that they sampled very slowly, and I can see the reason why. If you have a parameter up here in the parameters section that doesn't have a sampling statement down here in the model section to express its prior, and by sampling statement I mean it's on the left-hand side of an equation that has the tilde on it. So there's no line down here in the model that starts with sigma tilde. When that happens, Stan will assume that you want a uniform prior on that parameter. So if we have a parameter here, it's lower bounded at 0. It's going, if we don't express it's going to express, implicitly have a prior that ranges from 0 to infinity with a uniform value. If you have, that tends to yield really bad sampling, or at least very slow sampling, because it has to learn that, oh, actually it doesn't need to be way out in the range, in the upper ends of the range. So better would have been if I actually explicitly put sigma and put a Kashi on it of 0, 20 or something. Just like so. So otherwise, once we've set a prior on sigma, regardless of whether we actually impose an explicit prior on sigma or accept the implicit uniform on sigma, had we not expressly put a explicit prior on it, sigma is used down here again as that error variance in measurement, such that for every y is assumed to be normally distributed with that same error variance or standard deviation here. However, every y has a potentially different value for where its center is, for what its mean is. And that's dependent on these other parameters that we define. So it's easier to step through the actual parameters here. So the intercept here is just again, the center of the population. The effect would be the center of the effect population. We're going to have people vary from this intercept value from one person to another, and vary from this effect value from one to another. But these just specify where that population's mean intercept is and where that population's mean effect is. I actually should have put intercept mean and intercept effect, effect mean. That probably would have been a little bit more explicit. I'll leave it as is so we don't get confused if we look back. To specify what the variability people are around the intercept that we specify, we talk about we define a parameter, intercept SD, and to talk about the amount of variability we expect from one person to another in the manifestation of the effect, we have effect SD. And just as when we actually generated the fake data, we had to actually create samples for each person reflecting that person's intercept and that person's effect. We actually have to create two sort of storage variables to reflect each person's intercept and each person's effect. So in the end, we're actually going to be doing inference not only on these population level parameters, so where the intercept is centered, where the population effect is centered, what sort of variability we have in each of those, but we'll also get estimates from each person as to what that person's intercept is and what that person's effect is. So by looking at the distribution of those, you can actually check some of the assumptions of your model, like are they normally distributed, or do you have strong outliers, that sort of thing. So if we look at the model section now, we'll see that the first little section is the priors on all the population parameters. We already talked about this prior on the error variability. We can say that's the intercept. Again, we were thinking about IQ scores, so we expect a reasonable prior for the IQ scores is a mean of 100 with some variability, some reasonable amount of variability in what we consider credible. So I guess I have 10 here for some reason. We may debate on how broad that credibility distribution should be. Here, for example, 20 would not be a super credible, 120 would not be considered very credible, whereas in previous examples we actually had a normal distribution that had a standard deviation of 20, in which case 20 would be reasonably, 120 would be reasonably credible. But for present purposes, since I already compiled this model and had it sampled, we'll leave it as 10. The center of the effect distribution for the population is modeled here as having centered on 0 because we actually don't have any strong feelings, or we probably don't want any strong feelings about whether there was an effect in the population or not, just to appease any critical reviewers. If we did have a strong, say we actually did think that there was we expected an effect of 10 IQ points, we could put 10 in there, and that would accurately reflect our existing beliefs, but maybe there's somebody out there that is hypercritical of the literature on which we base those beliefs, that belief of a 10 IQ point effect. To appease those people, it's generally considered most appropriate to center your the effects that you have that are of particular inferential interest, center it on 0, so that's you can appease skeptical folks. So we've got normal distributions on both the intercept and effect in terms of the our prior. For the distributions reflecting the for the priors reflecting the parameters that are variance parameters, they can't be normal because, of course, you can't have a negative variance estimate. So we'll use the Cauchy distribution, and the fact that it's lower. We've expressly said that the lower bound is 0. This is going to be a half Cauchy distribution, so it's all the positive values. Having it a half Cauchy versus just a half normal, if I'd put normal here, that would have worked just as well. For variance parameters, we tend to use Cauchy because it's, again, it's a t distribution with degrees of freedom 1, so it has really fat tails. So with a normal distribution, it falls down to having low credibility to larger values. That it declines very quickly, whereas with the Cauchy distribution, it declines rather slowly, and there's still sort of a decent amount of credibility for even very large values. So we'll have these. What's possibly important, before I said that the distribution, or the prior distribution, the shape of the distribution we use for expressing the prior on the error variance, here the Cauchy doesn't really make a whole lot of sense because we actually don't think that 0 is a really tenable value. It might make more sense to actually say that it's a log normal. I think that's yeah, that is. But we'll leave it for now because I haven't explored the consequences of not using a Cauchy, and Cauchy works for examples we have so far. Here, it actually does make sense to use a Cauchy distribution from the perspective that for example, if there's no effect, then we wouldn't expect like a large standard deviation of effect. That would I guess maybe there's a variety of useful reasons to have 0 as the most credible magnitude for the standard deviation. Particularly in the context where there's no effects, then you'd actually expect there to be no additional variance contributed by that effect. It also has nice things whereby it makes it so that if you have an outlier in the, say, one subject has a super large effect, it tends to pull that person back in to be a little bit more, I guess, less influential on your estimate of the population effect than otherwise would be. It's a bit more of a nuanced thing. I thought I'd just mention it, seed your minds for future reading. So once we've established the priors on all these population level effects, we can, down here, essentially do the same thing that we did up here when we're actually generating data, which is we assert that each subject's intercept is normally distributed with a mean of intercept and a standard deviation of intercept SD. And each subject's effect is normally distributed with a mean of effect and a standard deviation of effect SD. So having generated each person, or expressed how each person's intercept and each person's effect is assumed to be distributed, we can now go through each observation and explicitly say, okay, for that observation, get the intercept corresponding to the person that contributed that observation, add that to the effect, the product of these two things here, which is the effect for the person that contributed that observation times the contrast for that observation. So hopefully if we go over to R, yeah. So it's for every observation, so this is going, there's ny total observations. So what this is doing is this is looping over every single observation. Every single observation has a contrast associated with it. So we get the, say, the first observation. Let's actually take a look in R. So head, what did I call it? Head. Oh, actually, I think I just... All right, so this first person is in condition A, has the value of 107, and the contrast associated with condition A is negative 0.5. So what this last line is doing, it's saying that, let's look at that first line. So ny equals 1. That y value, 107, should be modeled as being sampled from a normal distribution with an intercept of whatever was, I guess, sampled as that subject's intercept. So that's what this syntax is, because there's a total of ns, or there's a total of 30 s-intercept values. So we're grabbing the whatever subject, the intercept value for whatever subject this current y is. And so that's the intercept value for that subject times the effect for that subject, or sorry, plus the effect for that subject times the contrast that thing is. So if it's, say, an effect of 10 that was sampled for that subject, and we have the contrast of negative 0.5, we'd say whatever their intercept is plus 5, 10 times negative, or I guess, what it would be? It would be negative 5. So, and then finally, sigma is common to everybody, so it doesn't have any subsetting or anything like that. Okay. So, I guess I didn't. Why did we recompile? Can anybody remember?
I think you just did it.
Oh, okay. Oh, right, yes, and then gotcha. Okay. So I'll go down. In theory, this is the section that would have compiled the model. Probably a good idea in general to save it so you don't have to recompile it in the future. When you come back, you can actually just run this load model.rdata, and that will put it into your workspace without having to have compiled it in that particular session. And we can sample from it. I'll show you the first little bit of what happens when you sample, because there's a few error messages that happen that I'll explain a little bit. All right, it looks like, oh, big red errors happened, but it's actually still going. I can even see in my CPU monitor it's still going. So let's actually read the error message. Informational message. So it's probably not actually an error. The current Metropolis proposal is about to be rejected for the following issue. And then stan, prob, normal log, scale parameter is 0, colon 0, but must be greater than 0. If this warning occurs sporadically, such as for highly constrained variable types like covariance matrices, then the sampler is fine. But if this warning occurs often, then your model may be either severely ill-conditioned or misspecified. Well, I see just one instance of this, and then it's still going, so it seems to be okay. So very often you'll get this, and that's because we're actually estimating variance parameters where we have this lower bound on it, and it just has happened to try a sample where it's precisely equal to 0, and it doesn't like that. So you'll see these occasionally, and it's completely fine. So I'm actually going to tell it to stop because I already did all the sampling for this. Let's go here and do R code again. So here's, if this actually did run through, we could save samples here and then load them again. I'll load them. And so if we just look at out, so it's, the format is a little off because if the names of these variables are sufficiently long that it pushes, we don't have enough space in the window to show the column, the last column here, so it repeats all the rows again, but this actually is all the stuff we need. What we see in a much bigger table than we've had in the past. The 4 things up here are things we kind of have seen in the past and expect, but now we've got these big long lists of really what this is. These are the intercepts for every single subject, or the posterior samples of the intercepts for every single person, and similarly the posterior samples for the effects for every single person. So it's a little hard to eyeball these intercepts and effects for every single person. You generally want to just double check that they all look like they're well sampled. The fact that these two sort of diverge a little bit, I haven't fully explored what that means. My guess is that they're a little bit of an outlier, or they may have an outlying observation. I have to explore that a little bit further. More critical is looking at these top ones that we are most interested in. So looking at sigma, what did we generate for sigma in terms of when we generated the data? I think I had it as 10. Okay, so there we go. So we've recovered that parameter pretty decently. The credible interval encompasses it pretty well. The intercept we had set at 100, and we've recovered that one pretty well. Not really surprising since that was the center of our prior for that anyway. The effect, our prior was, we generated the data using effects of 10. We set a prior on 0, but the posterior is centered on 10, which is what we generated the data from. So that's nicely recovered. And we've got this nice tight credible interval around the our temporarily forgotten but true value of 10. Let's check out the variance parameters, like how people vary from one to another in their manifestation of the intercept. So we had generated the data using intercept of 15, and it's actually getting pretty close to that value, and it has the mean of the posterior distribution is around 15. Ditto with the variance estimate of people's variability one to another in the manifestation of the effect. Well, it's precisely 3. That's nice. So having...
Just a quick question.
Yeah.
The n underscore f in your last column that's displayed there is very small.
Yeah.
For some of those.
So that's going to be more the case with these with these variance parameters. And we'll actually see, if we were to plot these, they're not very well sampled, so okay. I'd put less credibility in like the accuracy of these bounds here, but they're not actually that, first of all, it's not really that inferentially important to us what these are in the first place, at least yet. And it tends not to affect inference that much when you do have poor sampling of these variance components.
Okay. And that would just be fixed by doing more
Yeah, you could just,
and
more time would give you more
Okay.
samples and better estimates of the actual, what are credible values for that thing. So, going back to our code, we can take a look at what I have down here. Now, if I'd shown you before how to use the ggmcmc package on visualizing things and getting the samples out of this out object, but we've got a lot of sort of parameters that we're not super interested in, at least not at this stage of what I'm teaching you, this s-intercept and s-effect stuff. So I wrote a little function that's included in your code on how to get the samples out, but then only keep the parameters that you actually are interested in. I won't go through all the stuff here, but the actual usage of it is you give it the object that's the stan, the output from stan. Might even just put explicitly label the arguments. And then you give it, the second argument is called parse keep, and in there you give it a vector of the strings corresponding to the names of all the variables you want to keep. So so if I run all this, it'll just keep those things that we're actually interested in. We can actually take a look at some of those samples. Let me go to R. I'll make this big. And we can see that for the effect, intercept SD, and sigma, I mean, it's pretty decent. Might want a few more samples. There's that effect SD where we noted that the number of effective sample size is pretty low, and indeed we see that the partial versus complete has a bit of a disparity in the shape of these distributions, suggesting that we don't really have a good sense of this distribution yet. And similarly, if we actually look at the autocorrelation, which is something that contributes to the contribution of that number of effective samples, we'll see that the effect SD is strongly autocorrelated, which is why we have low effective samples. But the other ones are pretty decent. And if we wanted to actually look at the condition means and the different scores, so technically we already know the different scores from the output when we just look at out and look at the effect row here. So in theory, that's the different score between the two conditions. But we can actually explicitly compute that as well. So let's look at the mean for condition 1. So we can compute that by the value. So we've got this data frame called samples. We'll just take a look at it again. I think R opened up in a different space. And there we go. Let's make it look. All right, so if I look at head samples, it's this data frame where for each chain, we only ran one chain, in each iteration we'll have a value for each of the parameters that we have. So I can say with that samples data frame, take the values corresponding to the intercept parameter and add to them the values corresponding to the effect parameter, where each effect parameter is multiplied by -0.5, and that'll give us the expected, or the posterior samples for what we would expect in condition 1. And ditto, we do the same for condition 2, but instead of -0.5, we multiply by 0.5. That'll give us condition 2. And so then we can actually look at the posterior distribution of what we would think of in terms of where the condition 1 mean is. So centered on 96, but with a little bit of variability. And ditto condition 2. centered on 106. And if we actually explicitly compute the difference score there, it's going to be the exact same as what we had up in the output table for that row corresponding to effect, about 10.56, and with that with the credible interval around it. If you're ever visualizing these conditions like this, usually, so when I tell it to create the condition where for each iteration I give it the corresponding value estimated for the intercept parameter, and then the corresponding value, value corresponding to the effect parameter, and do the math that way. What that ends up doing is you've got some uncertainty or variability in your posterior associated with the intercept, and some variability associated with the effect. If you're doing a visualization for, say, a scientific publication, very often you actually don't care about the variability associated with the intercept. You only really care about the variability associated with the effect. In psychology literature, there's a whole thing about within subjects confidence intervals or within subjects error bars, and that's what this is all about. We actually don't care about the traditional approaches to computing error bars are tend to include variability we don't care about, the intercept variability. There's various approaches to trying to solve that. This is one solution which I think is the best and most straightforward, which is to, when you are computing these posterior distributions, you just ignore the variability associated with the intercept by just getting its mean. So you have a single value every time you're computing a sample, a condition, a cell's value. You have a single number that you're using for the intercept, but then you have varying numbers you're using for the effect. So the consequence of doing that will be shown here when I recompute these and then look at the credible intervals. Up here we had condition 1. Its credible interval goes from about 91 to 101, whereas down here the credible interval is 95 to 97. So if I were to plot those, the sort of error bars and the sort of difference between I guess the size of the difference between the medians relative to the size of the credible intervals on each would generally correspond to what we would conclude if we actually explicitly computed the credible interval for the difference score. There's arguments about that it's a little bit misleading and that this is not really the credible interval for an observation in that condition, particularly when you zero out or ignore variability in the intercept. I find it useful. Anyway, that's just an aside. So that's an example of a very simple hierarchical model where, let me bring up the data generating code again. Where, again, you have a number of people, each observed a number of times within each of 2 conditions. And critically, when generating the what each person's intercept is and what each person's effect is, we did these 2 things independent of one another. So what you've effectively assumed there is that, well, an alternate scenario for generating data and for what might exist in the real world for your real world data is that there might actually be a correlation between these 2 things. So maybe people with low IQs are more strongly benefited by an intervention than people with high IQs. Traditional frequentist stats can't take that into account, but a mixed effects model can explicitly, the traditional frequentist within subjects effects can't take that into account. There are frequentist mixed effects models that can take that into account and explicitly estimate the correlation between these 2 things that might describe a person. And certainly in the context of Bayesian models, we're going to take a look at a version that estimates that possibility for correlation. Before I jump ahead, though, does anybody want me to review anything about this idea of the hierarchical model? All right, so we'll jump straight in. Yeah. Oh. Yeah, that was well, yeah. So up here, when we're computing the, we're trying to compute a credible interval for observations in condition 1, and we go through all our posterior samples, and we add two things. This thing has variability from sample to sample, and this thing has variability from sample to sample. So when you add two things that each have their own variability, the sum has an even more variability. But generally, when we're doing inference, we actually don't care about the intercept variability, or when we're doing scientific inference, we don't really care about that intercept variability. And so if you actually do this alternate way of doing the computation where we collapse all the samples, the estimate for all the samples, intercept into a single mean value. So that's a single value, it doesn't have any variability, and take the sum of that and this other thing that does have variability. The sum of something that doesn't have variability plus a thing that does have variability is simply the variability. Will have a variability corresponding to simply the variability of the thing that does have variability. That was a really long sentence. So you're basically zeroing out any variability associated with the thing that you're not interested in. So yeah, it's a little bit controversial, but if anybody has encountered the discussion of error bars for within subjects designs, that is effectively what people have been attempting to achieve with the various solutions they've been proposing. In this context, you can do it directly. So we'll move on to number 12. Oh, sure. So here, we're going to generate some hierarchical data. Double check that R has started there. So same as before, we've got 30 people. Each is going to be observed 5 times in each of 2 conditions. We're going to have just a common trial-by-trial error for each person. Same values for the intercept mean, intercept SD, effect mean, effect SD as before. But now we're going to generate data that is from a population that has a specific correlation, between what a given person's intercept will be and what a given person's effect will be. So you don't really need to know much about this section of code. This is just how you generate this fake data in R. When you're actually observing real data, you don't need to know like this use of MDR norm, etc. Once you, let me just run all this. So having generated this thing called subject parameters, I just want to double check because I'm generating fake data and I don't want to mislead you guys, that it has the properties we asked it to have. So I'm actually going to copy these 2 lines. So subject parameters ends up being a matrix. With 30 rows and 2 columns. So 30 rows, I had 30 people, so row must correspond to people. 1 and 2, that's going to correspond to the intercept and effect. So if I look at the mean for the first column, 98, very close to what we asked for, of population mean of 100, and mean of the second column is 9.5, very close to what we asked for as the population mean for the effect. Ditto if we look at the standard deviation of the first column, 13, very close to 15 is what we requested. Standard deviation of the second column is 2.65, very close to the standard deviation we requested. Finally, critically, the correlation between the two columns, 0.76, which is very close to what we requested. So this is just validating that this sort of complicated code of generated data that corresponds to a scenario that we wanted to. So we've got some data here where we've got individuals varying from one another in terms of their overall IQ, individuals varying from one another in terms of their response to some manipulation, and then finally a correlation there between. And we'll generate data just identically as before. Package it up for RStan. And then, because I've already actually run the model, I'll load the model, but I've already run it, so I'll load the data. And while that's loading, which is probably already done, I'll take a look at the RStan code. So, maybe I'll pull over, pull up the code from before to highlight the differences when you start implementing correlations. All right, so on the left is no correlations. On the right is starting with correlations. So if I add a line here, you can see that the data that's coming in the same as before. First line here, lower equals defining a sigma value. Well, that's identical as before as well. Here we see two parameters, intercept and effect, whereas I've switched to something like the matrix stuff, where now I have a single vector with two elements. The vector's name is mu, but these two elements correspond to what we would have had before as intercept and effect. Similarly, I've got two parameters in the no correlation version, one in intercept SD, effect SD. Over here, I've got a single vector, same lower bound of 0, named tau, but it has two elements that are going to correspond to what we had over here as two separate parameters. I had two vectors over here to collect each subject's intercept and each subject's effect. I can actually do the same thing by having a vector of length 2, calling it S mu, and then having yet more stuff on the right-hand side. What this bit is it's saying that I have an array. So this is a vector of arrays. So you think of it just as this is a list of length 2. Each item in the list has length of ns. I can't recall why that's better than having a matrix. I think in maybe the next version we'll be creating a matrix, but just for these purposes it's not super important to know why, but we just have a slightly different way of setting this up. And finally, a new thing is that we're actually having as a parameter a variable that is a correlation matrix. This 2 means that there's two variables that are correlating, so really it's a correlation matrix is a 2x2 table with identity along the diagonal, and then you have one other thin box to fill with value that's going to vary between -1 and +1. So we're going to call that correlation matrix rho. So before we had a thing called sigma. We still have sigma. We still, I guess, as before, I failed to actually set a prior on sigma. So probably a good idea to put a prior on sigma there. Otherwise, it's implicitly uniform, which just makes your code slow. And otherwise, we had over here 2 lines, intercept and effect. We can still have 2 lines, one referring to the prior reflected on mu1, the intercept, and the prior on mu2, which is the effect. because we previously had two lines to reflect our priors on the intercept SD and the effect SD, because we have the same prior for both, you can just put, even though tau is a vector of length 2, you can tell it to have, you can use a single line to express that you want the same prior for each element in that vector. And then we also express a prior for what the correlation should be. It turns out that if you put LKJ core 1, that makes for a uniform prior across the range that a correlation can take, which is -1 to +1. If I actually put like 2 or 3 or 4 larger values there, we'll actually start having a prior that's more strongly centered on 0 or concentrated around 0. So 1 is completely flat, and the other values are more and more concentrated, in case you want to reflect, I guess, larger confidence in exactly 0 correlation. Starting with just a uniform prior on 0 is probably a good, it makes things sample a little bit, I guess, less well if there sort of is truly not a 0 correlation, but it's, for these simple models, it's not too bad. I skipped over these few lines up here. So in the model section, we're actually going to create a new variable, so we have to initialize it. So it's a matrix that's 2 by 2. We'll call it Z. It's not a very informative name, but it's because it's actually not going to be used very directly. So this is just used in helping get the, I guess, stuff that happens down here to work out to have, in the same way that when I looked at generating the data, I had to define this matrix corresponding that has certain properties of its values to get out the proper standard deviations and correlations for each cell of the design. Here is the same thing. I've got a row, so it's this correlation. I've got standard deviations, and it's going to combine them in a way that makes it useful to generate samples from a multivariate normal distribution. So having done that, we can actually skip down. So in the prior one, version with no correlation, I just independently sampled a subject intercept and a subject effect, each from normal distributions. Here, I iterate over subjects, apply to each subject. So remember we had, I guess what this up here when I say vector 2, subject mu, and then in brackets and s. This actually creates something that has, it's actually a list of length ns, each of which is a vector of 2. So the first time this goes through, it's going to get the first subject, assert that subject's, those 2 entries in that vector are distributed as this multivariate normal distribution. So with the means of each of the columns of 1 and 2, of mu, and a covariance structure of this Z thing. And I'm going to make this bigger so I can actually see. So this establishes the same thing as before, where we had an estimate for intercept and effect for each person. Now we still have an intercept and effect for each person. They're just stored in a vector for each person of length 2. And this part has implemented the idea that there's a possible correlation between those 2 parameters. And then finally, this bit down here is the exact same as we had before. We have for each observation for y, we get the corresponding person's intercept, add that to the corresponding person's effect times the contrast for that y. And then everything has a common sigma, so sigma's there. So if I look at what we got out here, again, because we're estimating something for each person for an intercept and each person for an effect. Oh, that's actually not, because we didn't actually have these variables. So this is right. This is the, all right, so we will have to sample. Or did I just, I didn't actually load, I didn't change the working directory.
Mm-hmm.
So I loaded the wrong, that's much better than not having sampled it properly. All right, so probably unnecessary, but I'll load them all. And definitely necessary is to load the data. All right. So before we had S-intercept and S-effect. Now we've just got SMU, and it's got 30 entries, but each entry has a 1 and a 2. That just corresponds to the intercept and effect for each person. And then up above, we've got sigma. That's the same as before. Mu1 and mu2 now. So mu1 is the intercept. So 99, very close to the 100 that we asked for. 9 is very close, and mu2 is the effect. 9, very close to the 10 we asked for. Tau, 13.90, very close to the 15 that we had specified in the data generating process. Tau 2 is 5, and that's very close to the, I think we had 3 as what we asked for. And the correlation, 0.73. And critically, you see that the credible interval on that correlation excludes 0. So it is sort of adequately seen that there's a correlation between these two things. Otherwise, just go to the R code and see. So if we wanted to just take a look at the samples for each of these things, I think I showed you in a previous version, but the names it gives them, instead of wherever you see a parenthesis, or sorry, a square bracket here, you want to put a period. So, and critically, these rows, since it's a symmetric matrix, you only need one of them. The diagonal, I don't know why they even bother spitting that out, but you don't need the diagonal elements, so 1, 1, and 2, 2. And of the non-diagonal elements, they're both the same, so you only need one of those. So to define our function, grab things, and run it, and look at that. So this is actually a sample a little bit better than the last example that I had. Maybe I had many more samples in this, I can't recall. I'd actually maybe want to sample it for a little longer. And autocorrelation, there's still a little autocorrelated, if I recall correctly. But again, the autocorrelation is used to influence the number of effective samples, so it's not an independent diagnostic unto itself. So if you have enough effective samples, then you don't need to worry if it's still autocorrelated. And otherwise, the code down below here is the exact same as before, where it's picking out the conditions, and you have an example where it includes the intercept variance, so that's mu1, or it collapses the intercept samples to a mean and uses those instead of each individual sample, so thereby zeroing out the variance associated with the intercept. But otherwise, that code is the exact same as we had in the previous example. So, any questions about the idea of adding the potential for correlation amongst your parameters in this context? So again, there are some frequentist, sort of newer frequentist tools that allow you to evaluate the same sort of model where there's correlation. The traditional tools certainly can't, though. The final bit of prepared code that I have for you. Let's close some of these windows. So we'll open up 13. And, yep, change my working directory. And, so the data generation here is the exact same. but I'm giving you an example of structuring your data for input to Stan, and then the code in Stan for the matrix version of this, which makes it easy to extend and have more levels per manipulated variable and more manipulated variables and interactions there between. So, I've created some data. Head data. Looks exactly as before. We've got a bunch of people with labels, unique labels. Each person has participated in each of two conditions, and there's multiple observations for each of those two conditions. We're going to use the matrix version. So instead of just a single thing we're passing into the single vector we're passing in as the contrast for that condition, we'll create an actual matrix that we'll pass in. So we'll create X as a data frame, has one column that's just all 1, another column that encodes that first contrast, well, first and only contrast in this particular example, turned it into a matrix. We have to create another matrix called B. This is partly because, well, you could say that I wanted to give you an example that you could take away and apply to both your fully within subjects and your mixed within and between subjects paradigms. You could also say that I haven't figured out how to actually do the simply within subjects matrix version. It hasn't worked for me. So we're creating a thing called B. Let me double check. Did I figure that out last night? Oh, I did. Okay, so we can ignore B. Yeah. So ignore what I just said about B, because I did figure it out. So you don't need to have B there. So I can take B there, out there, and take B out there. Yeah. Well, the corresponding Stan code didn't pay attention to B at all, so I'll give you code that has that extra nuance of allowing between subjects variables as well. And in fact, we may walk through it in a moment. But for now, we just create this matrix X that we'll use. And in terms of packaging things up for Stan, it's similar as before. We've got NY, number of just observations, and X, that's the number of contrasts that we have, including the intercept, and S being the number of unique levels of ID. Y is just the column of values of data. X is that matrix of contrasts. And S is the unique, or those labels for each data. So package that up for Stan. In theory, we could compile, but instead, I will just load the model that I already ran. And in theory, we could sample, but instead, I'll just load the samples I already ran. But before looking at those samples, let's actually look at what the matrix version of this within subjects Stan model looks like. So, very similar to before in that we have the NY and X and S, X, and Y. The only difference here is instead of contrast 1, we've got X, and instead of being a vector, it's a matrix. Again, similar as before, we've got the sigma, which is just a single value, mu, which is a vector of length. Before it was of length, well, 2. Here, I let it be of length nx, because if you had more data coming in of even more complexities, so more contrasts, you could just reuse the same code. Ditto tau is a vector of length nx, so for this example it's 2. And rho is an example is a correlation matrix of size nx, and that means you have each dimension is nx with a ones along the diagonal. Finally, each person is going to have, so now we have this matrix, which is a little bit nicer to see. So for each row, each person, you're going to have this many things estimated for that person. So here we only have 2 things, an intercept and an effect. So it's going to be a 30 by 2 matrix. We have the same thing as before, though, when we hit the model. We sort of define something called Z, and that's just being used for establishing the covariance matrix for sampling the multivariate normal based on your requested distribution of or prior for rho and the prior for tau, tau being the standard deviation of people from the various effects that we're estimating. Again, we forgot to actually put a prior on sigma, so sigma, and we'll use the standard prior for sigma we've been using thus far. And before I said mu1 is distributed as normal 110, same thing here. And then I had mu2 is distributed as normal, mu0, normal 0 and 10 or 20, I think. Here, just again to generalize for the situations where maybe you have more contrast to reflect maybe a 2 by 2 or a 2 by 2 by 2 or a 3 by 2 or something like that. I just, instead of trying to go through each contrast and give it its own prior, I just say, okay, the intercept has this prior, but everything else has a prior centered on 0. I think for previous examples, I had the intercept prior as having a deviation, standard deviation of 20. Probably should have had that here, but just forgot when I compiled the model. So I don't want to resample, so I'll leave it as is. Tau, again, it's a vector, but I want to assign the same priors to each of its elements, so I can just put it as tau is distributed as, and here we're using Kashi. I don't know how to pronounce that. And finally, yeah, Kashi. And then finally, of course, we've got the prior on the correlation. Again, this is a correlation matrix, so we'll just assume a flat correlation matrix. And otherwise, everything's pretty much the same as before. We fill this matrix reflecting each person's, I guess, coefficients for each person's intercept and various effects by expressing it as a sample from a multivariate normal distribution with mean mu and this covariance matrix that's being formed by the rho and tau. And then finally, we iterate over the data, saying for each y value, model it as being normally distributed with error variance of sigma and a mean corresponding to this thing, which is let's see, is it similar to what we had for the one of the simpler models we had? Similar, we're multiplying here we are multiplying a vector by a matrix, and here, I can't remember why, but there was a reason why we had to have this slightly different format where we do a transpose here. But X is a matrix. I think it's because S is a rho vector. I can't recall. But this is certainly a lot easier to type out, particularly for more complex designs than the larger sort of full expression of things. But we should get out very similar results. Frankly, it should be identical as before, where we have sigma, mu1, mu2, tau1, tau2, rho for the full 2 by 2 matrix, and S mu's for each person and for each contrast we gave it, so intercept and effect. And yeah, everything should be the exact same, so I won't bother, but if we went through this, you'd actually get the exact same values as we had before. The model just had a slightly different format for how it was doing the math to allow you to extend it to more complicated designs. Well, because in the real world, things can be correlated. And so, I guess for two reasons. One, just to more accurately reflect the potential for relations in your data that might happen in the real world. And two, if you're actually interested in, like, I guess this would be in the world of what's called individual differences analyses in psychology land, whereby maybe you actually are interested in the phenomena of whether somebody's mean RT correlates with their queuing effect. Maybe that's actually something that pertains to theories you have about how those two things might be caused to be related in the brain. But even if you're not explicitly interested in that correlation to see whether it's non-zero or not, including the potential for that, if you have those two phenomena in your data, then it makes sense to actually include the possibility of them being correlated, because if they are, which possibly could be in real life, then you want your model to most accurately reflect the reality, and the potential reality.
If there is any correlation between knowledge, it can help you.
Yeah, yeah. So really, what it comes down to, what it comes, if there isn't, it doesn't hurt. It may make your sampling a little bit less efficient. It may cause the computer to have to run a little bit longer, but it doesn't hurt otherwise. You could think of the versions of the model where you don't try to estimate the correlation as instantiating a firm assumption of zero correlation, and that's probably never true. So it's good to include it.
It's not necessarily something you would report, though, because you're not necessarily inferentially interested in it, but at least you're accounting.
Yeah, I mean, it's become very vogue to report that you allowed it to have this potential for a correlation structure, mostly because this is one of the reasons why people started using mixed effects models or hierarchical models, was because they realized that you could start doing this. So you'll see a lot of reports about mixed effects modeling explicitly talking about what the random effect structure is. That's really what they're talking about. They're talking about what is sampled in terms of, again, we have subjects that have intercepts that vary from one another and effects that vary from one another. And whenever you have that, you could make a statement about whether you also then allow there to be a correlation or not. The general consensus practice from the non-Bayesian world is to always try to include the correlation. Now it tends to be, with some of those tools, it takes a long time to do the math for the frequentist tools to do the math to figure out what it should believe about the correlation. Whereas the Bayesian tools I find are a little bit faster. Yeah. Now, I guess in the little time we have left, I obviously didn't pre-compile or do any additional examples here. This is number 13. But I want to show you some nuances that you can make on this or that you'd be very likely to want to make. So I'm going to create another one. I'll call it 14, and I'll provide these to you after this. All right, so I've copied that. So far, I've expressed that one of the benefits of doing the hierarchical version is that you can account for this correlation that's possibly there, and it really doesn't hurt. And frankly, well, even if you're not doing a correlation, you can account for this hierarchical structure. It turns out that, and we've so far been only dealing with data that is Gaussian distributed, so we've always had y as distributed as normal and then some stuff. But where these mixed effects models or hierarchical models really shine is when you have potential for non-Gaussian distribution of error. So one thing that typically comes up in the context of psychology is that we have people doing things and we mark them as being either accurate or inaccurate. And very common, the sort of first step in data manipulation is to compress all those answers down to a proportion. So you have in one person in condition A, proportion correct, in that same person in condition B, proportion correct, and you try to do some sort of inference as to whether there's a difference in the proportion correct between the two conditions. It turns out that when you have that, particularly when you have more complex designs like a 2x2 or like multiple conditions, collapsing to a proportion and doing just a standard within subjects ANOVA on that sort of thing will actually give you wrong results, or potentially wrong results. So the general suggestion these days is to you have binomial data and you have collapsed it to a proportion. The alternate is to treat that binomial data as binomial. Use tools that can deal with it on a trial-by-trial basis. So what we will do then is we'll generate some data. I'll do it on the fly. Same structure as before, but this time we actually won't need sigma. I'm going to delete it. Exactly. So we're not going to have a Gaussian distribution of error from trial to trial. We're going to have ones and zeros to trial from trial to trial. I'll still generate the same covariance matrix. But here, I said our norm, and one of its parameters was sigma. I'll take that out. And just to refresh my memory, let's forget. So size 1 and 2. Okay. I was just trying to remind myself how this works. So we're going to model this instead of samples from a normal distribution. So instead of k samples from a normal distribution, we're going to say it's k samples from a binomial distribution. And the binomial distribution is defined, with having number of samples. And if I put 1 here, that means it's going to be 0 or 1. And it wants a probability as the third argument. But here I have something that's going to take a continuous value. A standard assumption is that the binomial proportion is actually a something that takes a logistic is a logistic function of something that is Gaussian on something that's Gaussian on. You take something that's Gaussian and you you convert it using the logit transform. So let's see. If I had to value 2 on some real domain, I can. Let me step back a bit. Let's say that there's some thing in your head that causes you to be biased, and that thing can have any value from negative infinity to positive infinity. So you have some sort of scale of biasness. To transform that biasness into an actual observation of whether you say 1 or whether you say 2, 1 or 0, you assume that that real valued continuous negative infinity to positive infinity scale is transformed into log odds scale to create this probability. They're using the log odds transform. So about 2. So for example, if you had a real value of 2 in your head, that yields a probability of 0.88. Real value of 3, you'd have a probability of 0.95. Real value of 4, probability of 98. And you see, you actually never get to 1. Well, there we go. get the 1, but that's because of machine precision. So 10. You get increasingly close to 1. 0.5, or sorry, 0 is the same as the probability of 0.5. And it's symmetric around there. So if I say p-logis of -2, it's, I guess, that is as close to 1 as this is as close to 0. So it's symmetric around 0.5. So yeah, we assume that whatever thing is happening on a real scale is then converted by the logit transform into a binomial scale. So we'll generate data that way. So let's see. These numbers we had up here for generating our data, that's really, really big. So let's say people have on average 1, which is about an 88%, say, accuracy. Intercept, say we have as varying from one to another by 1. The effect will have as a effect of 0.2 on the log odds scale and 0.1 as the variability from one to another, again, on the log odds scale. So let's actually go up to set seed, generate data. We should have 1s and 0s throughout the data, reflecting each person's performance on each of many trials within each of those two conditions. And again, I could collapse those down to a proportion per person per condition, but I'm not going to do that. Instead, going to do the matrix notation, combine it together, and I'm going to go look at that model. And the only thing I need to change when I go from the current version here, which is the Gaussian model, I get rid of sigma because we're not dealing with that thing anymore. So that's nice because it's one less parameter to estimate. Instead of normal, I say binomial. And let me just double check my recollection. I think it's linear regression. Bernoulli. There we go. Bernoulli. And I have to tell it that to do the reverse of that. Well, it's actually the exact same, in the same way that in the generation of the data, I do binomial of something that's being, well, I do a p-logis and then a binomial. Here I'm doing an inverse logit, which is the same thing as p-logis, and Bernoulli is the same thing as our binomials. Bernoulli samples, binomial samples. So, let's actually see how fast will this compile. Oh, okay. Inverse logit. Oh, I must have. Anybody remember how to spell Bernoulli? Okay, there we go. Oh, in fact, there is a, yeah, you can, instead of doing this, yeah, it's explicitly he was telling me that instead of doing Bernoulli of something that in turn inside is applied this, you can do that. So I'm going to do that. Let's see how many errors now. Okay, unknown distribution. Oh, so I was looking at this, but really what's happening is going on up here is that it doesn't like, oh, it just wants like how many samples is happening here. Yeah, oh, it's getting at 0 real. What's going on? Because these examples only have one argument. Oh, so there's, for every time you see a sampling thing, it actually implicitly calls something like that, and it uses something like that behind the scenes that they give you the hooks to use it if you want. So yeah, the statement says that it was trying to do this, but really that is because we called this much of it. And this is, the whole thing is called implicitly when you call just this bit.
So it looks like the problem is that this passed a real instead of an integer.
Well, no. So I wonder, do I just have to define like how many samples? I almost don't. I wonder if this, it's not actually. Yep. I don't know. Let's go look at the code that. This is some code that I wrote a while ago, but I wonder if like y is just a vector.
the apostrophe doing at the end of that phrase?
Transpose.
Ah.
And I hate that they use an apostrophe for a function. I'd rather it be like transpose this. But yeah. And again, that has to do with the fact that it's, I know, let's actually try, I'm going to grab, comment, pull the entire file out, and go grab the version 12, where we had a correlation, but we didn't do the matrix stuff. Okay, so there's 14. So again, I'm getting rid of sigma, and so y is the new logit. Nothing else I need to change. Okay, it's telling you that I put in a real as type 1 and a real as type 2. I wonder, is this... Yeah. I'll try one other thing that's... Oh, I know. Because it doesn't like... So when you create a vector, it automatically... So I initialized y as a vector. It slightly... Well, it automatically initialized all those entries in the vector as reals. So if I said int y this, it's going to create an array of ints instead of a vector of reals. Let's try that. And I'm going to get rid of this. Yeah. No. Yeah, it's one slightly annoying from people that come from a don't really pay attention to data types world of compiled languages like R. When you come to interpreted languages like R, you come to a compiled language, it suddenly makes a lot of it makes a lot of difference what you initialize things as. All right, so I'm going to close this. Close that. Okay. Should be able to run that. Whether this even, well, certainly it'll compile by the time the session is done, but I'm not sure if it'll sample by the time it's done. Other things that this general format, particularly with this matrix version can do. Again, we had the example of having a Bernoulli there. You can have like a very common thing, particularly for well, in like the psychology, is to have one of your contrasts be a like, for example, the temporal order judgments. You have one thing preceding another by some amount. So on the left y is square came first, square versus circle, square came first. And on the right, you'd have some set of conditions plus the amount. One of the contrasts is simply the amount by which square came first. This would automatically do that psychophysical function where it's that sort of S curve that we expect. And the intercept difference parameterization would, well, anything that is a, let's see, yeah, that would independently characterize the shift versus the slope of that psychometric function. Yeah, I don't think you'd need anything further to separate those two. Well, actually, you might. You might not want to do the Bernoulli logit. You'd want to do unit. That's the unit normal distribution. You could use the cumulative. Yeah. You would need to do something slightly different to do the psychophysical. It would be something like Bernoulli, and then it'd be like normal CDF, and this would reflect, things here would reflect the influence of variables on the shift, and then you'd have something different here. Talk about influence of the variables on the slope, so you'd be able to reflect those independently. And yeah, well, very common in reaction time research is to account for the fact that reaction times are non-normally distributed. So you could have a scenario where you again would be dealing with reaction times, in which case you'd have log normal. You'd have sigma again in here, but that would be sigma again on the log normal scale. That's pretty common. It's really common to have outliers in distributions. I talked about in the first session that you could use a heavy-tailed distribution like, well, Cauchy to characterize the single distribution that reflects heavy tails. You could also explicitly estimate like the proportion of outliers by having a mixture distribution, which I think you'd have. Well, there's a way to tell it that it's a mixture of two things with a mixing proportion that you can either specify or have as a model of a parameter of your model. Yeah. Obviously, I haven't. There's much more to play with. I'm just going to check to see if yeah. Okay, so this has started sampling, but it's going to take a long time to sample for a model like that. Yeah, I think I'm happy to having started you guys off on this journey. If you want to proceed any further and get stuck on anything, I'm happy to meet up again. Joe was talking about maybe like having a third session or whatever. But I think maybe I'll leave it as if you guys are interested in more content, maybe play with what we have so far, and I can meet anytime with anybody to talk about even cooler models or extensions.
Thank you so much for
Sure.
your time, Mike. My brain is full.
Yeah.
Appreciate it.
Yeah.